All right, so one last example that we're going to end up doing with spherical coordinates, but we're going to go down a couple different paths before we get there, and even then we're going to do one thing that is not the easiest way before we figure out how to do this. Why am I doing that? Because if you got this, so a contrived example would be if you got this on a test and we didn't tell you it was spherical, you'd have to figure that out yourself. And this is actually difficult to figure out which triple integral way to use this. We have 3 different coordinate systems. Worse, or not worse, but harder, better, because it's a better application. But if you got this in real life, if you're actually studying multiple integrals for physics or engineering, finance, psychology, economics, whatever, anything that will use this sort of calculus, you might get an integral that looks like this, and you might not be able to do it until you figure out the right way. Okay, so it's given to us in rectangular coordinates, so maybe if we don't feel like drawing a picture, we can just integrate it that way. It looks like it might be a little bit ugly, but let's just see if it's going to work. Okay, so I see no z's here, so when I integrate, I'm just going to get 18y as a constant times z, and I'll plug in the bounds. So I'll get something that looks like this. Top bound minus bottom bound, right? I'm just writing a little bit down, looking ahead, seeing if this will work before I fully commit to this method. And now I'm going to have to integrate this with respect to y, which is actually possible. So if I distribute that, and then I'm going to use 2 different u subs. So in the first one, on each one, I set my u to be the thing inside the radical. And I can do this, it's a little bit ugly. But that will integrate. And what I'm going to end up with is the thing inside the radical now to the power of 3/2, which with a bunch of ugly fractions out there, and this other thing inside this radical to the power of 3/2. And then, though, when I plug in these values for y, I'm now not going to be able to integrate with respect to x. So I could actually spend a lot of time on this rectangular thing, get all the way to the end, and not be able to finish it. So we cannot finish this integral unless maybe we use trig sub at the end, which maybe at that point you would try because you've invested so much effort into that already. Okay, so, but maybe not the best way, and they'll be pretty ugly trig subs anyways, so might as well convert. First choice for conversion in general is probably cylindrical coordinates. It's a little bit of an easier conversion, feels a little bit more natural since we know about polar coordinates. Okay, wait, I won't draw the picture yet. So I do need to draw a picture to make sure I convert it properly. So what is this region? Let's see, x goes from -1 to 0. Okay, y goes from, these are half circles, right? These are half of the circle of radius 1. So in the xy plane, we're in that region. And then z goes from, now by this point I recognize that's a cone with slope √6, and then that's a sphere with radius √7. Okay, slope √6, so pretty steep. And then radius √7, whatever that is. If that's -1, a lot bigger than that. Okay, so maybe this isn't quite to scale. Okay, and then z goes from one of them to the other one. And then we only want this half circle, because x is only going from -1 to 0. So we only want half of this ice cream cone, basically. The left half of the ice cream cone. Okay, converting to cylindrical coordinates then. Okay, that means I need the region in the xy plane. So I just need to check how big that circle is. So I need to do this thing where I intersect those 2 curves. So easiest way here, since they're both in z equals format, then we'll just set the z's equal to each other and actually square both sides. And this actually works out really nicely. So that's the curve of intersection of the 2 surfaces. Sorry, intersect the 2 surfaces is what I meant. So this is 7x squared plus 7y squared equals 7. So x squared plus y squared equals 1. So okay, that is actually the circle of radius 1. So the shadow of that exactly coincides with that boundary that we were given out here, which is great. Okay, so that means eventually I'm going to want dz, dr, d theta out here. So that means r is going to go from 0 to 1. Theta is going to go from pi over 2 to 3 pi over 2. And then z is going to go from these same guys, but converted to polar. So this is going to be root 6 times r. The root of x squared plus y squared can be replaced with r. And this is going to be the root of 7 minus r squared. And then, let's see, inside here, so y is r sine theta, and then we actually need an r as a part of this last thing, so we're going to have r squared. dz dy dx is going to be replaced with r dz dr d theta. That's what the r squared comes from. Okay, so we want to integrate that, and let's just try it. Okay, so we got, let's see, pi over 2 to 3 pi over 2, integral from 0 to 1. Integrate with respect to z first. There's no z's here, so that comes out as a constant, 18r sine theta z going from root 6. You can maybe combine multiple steps in one here, but it's a little bit safer to write an extra one, so I'm doing that now. You can do it either way. So pi over 2 to 3 pi over 2, let's see, integral from 0 to 1, we're going to plug these in now, 18r squared sine theta, the root of 7 minus r squared minus the root of 6r. R is outside the root here. dr d theta. Okay, is this easy or hard to integrate? The second term is no problem. Second term, once I expand, I have r cubed, basically, with a bunch of constants. First term, a little bit more of a problem. I have r squared times the root of 7 minus r squared. It's not an easy u sub. It's probably a trig sub. Okay, so that's hard. So maybe we won't do cylindrical coordinates. Maybe we need to do spherical coordinates. Okay, turns out this is also a little bit hard. But finally it will be doable. Luckily we already have a picture, so we can just work off the picture. Now we're down here, we're going to be working in spherical coordinates. Okay, so let's see what's happening. We need, let's see, 18, y is going to be rho sine phi sine theta. I need another rho squared sine phi, and then I'm going to have d rho, d phi, d theta. It's not part of that. Okay. Then I just need to look in this half ice cream cone where I'm integrating from, right? Okay, so rho is going to go from 0 to root 7. And then phi, let's leave phi for a second. Let's do theta is going to go from pi over 2 to 3 pi over 2. Okay, that's easy. That's how we get the half ice cream cone. Okay, and then theta, phi, I need to figure out what that angle is. The angle with slope root 6. And remember I said in the previous one, so I don't have a good triangle for this one. The triangle is 1, root 6, root 7. But I don't know what that angle is, or that angle. So remember I said the last time we had an arctan or a tan inverse. So phi goes from 0, because I want the top part. Actually, I lied, not tan inverse root 6, tan inverse 1 over root 6, right? Because I want, actually, the angle I'm looking for is the smaller angle, which will actually be equal in value to that top angle there. Okay, I think that's correct now. Okay, so now I start to integrate. It's going to be pretty ugly. Okay, pi over 2 to 3 pi over 2. I'm going to leave this here, tan inverse 1 over root 6. And then, so what do I have? I have rho cubed. So that's rho to the 4th, 9 over 2. is what the constant will be. Sine squared phi, sine theta, we don't leave that alone. And then rho goes from 0 to root 7. And then we've integrated with respect to rho. We still need to integrate with respect to d phi, phi and theta. Okay, so pi over 2 to 3 pi over 2, 0 to tan inverse 1 over root 6, and then putting in root 7, so phi to the 4 is actually going to be 49. 9 times 49. Maybe we'll just leave that there, do the arithmetic later. Sine squared phi, sine theta, d phi, d theta. Okay. Now this is ugly, right? We need the trig identity. Cosine 2 phi is 1 minus 2 sine squared phi. So sine squared phi is cosine 2 phi minus 1. 1 minus, other way around, 1 minus cosine 2 phi over 2. I rearranged that equation correctly. Okay. So once we make that substitution, we'll be able to integrate 3 pi over 2, integral from 0 to tan inverse 1 over root 6. I have another over 2, so this is 9 times 49 over 4 now. 1 minus cosine 2 phi, that's the sine theta, d phi, d theta. Okay, now I can integrate that. So that's pi over 2 to 3 pi over 2. I leave this all on the outside. I leave a sine theta actually on the outside. Integrate with respect to phi, so this is phi minus 1/2 sine 2 phi, right? And then phi goes from 0 to tan inverse 1 over root 6 d theta. Okay, how do I plug this in? Plugging in 0 will just leave me 0, so I really only need to plug in the top bound. 9 times 49 over 4 sine theta. Okay, nothing I can do here. This is tan inverse 1 over root 6. Let me look back at, so I guess what we ended up doing was doing the flatter version of the triangle. So that was phi. 1 over root 6 was the tangent. Hypotenuse was root 7. Okay, so that means sine 2 phi is 2 sine phi cosine phi, right? And then 2 sine phi is 1 over root 7. Cosine phi is root 6 over root 7. So this is actually 2 root 6 over 7. So with a little bit of geometry, I don't need to write sine of 2 times tan inverse 1 over root 6. I can write 1/2 times, I can actually figure out what sine of 2 phi was. So that's kind of slick. Still need to integrate with respect to theta. Okay, a bunch of ugly constants there. Excellent, our favorite. Okay, but actually we will integrate. So let's just write out the constants. 9 times 49 over 4, tan inverse 1 over root 6 minus root 6 over 7. Maybe we'll expand that later, maybe we won't. And then the integral is going to be negative cosine going from pi over 2 to 3 pi over 2. Okay. Interesting. Cosine of 3 pi over 2 is 0, and cosine of pi over 2 is 0. So if I did this correctly, the answer is 0, which I don't know why. You guys aren't the only ones that do this. I do this too. If I get an answer of 0, I start wondering if I did this right. So let's look back here. Is it possible that the answer was 0? What are we actually doing? We want this half ice cream cone. We're integrating 18y. So we're taking, in this region, both positive and negative values of y. And probably the same amounts of both, right? It's completely symmetrical about the x-axis. So yeah, I believe it. The integral should be 0. In fact, we didn't have to convert to anything. If we were really, really clever, we could have seen that from the original problem. We had trouble with cylindrical, but actually, if we had reversed the order of integration, integrate with respect to theta first, we would have seen that cosine theta. And we would have plugged that in and gotten 0 right away, so we could have done that. And then even when we did the spherical, the integration with respect to phi was hard, but if back here we had reversed this order of integration, we could have gotten the 0 a lot earlier. So 0 is certainly correct. There were ways to get it earlier if we were a little less naive. It's really hard to find those ways. It's really hard to do these problems the most efficient way possible the first time around. Also, it was good. I wanted to show you guys this for sure. This triangle. And then I wanted to show you this tan inverse. I guess that's a similar thing. I reminded you a little bit of these identities earlier, but it's always good to see those. So we did a lot of good math, and we were able to sketch a region and convert it to cylindrical and spherical coordinates. All right, that's the last example on that. Finally done with triple integration in rectangular, cylindrical, and spherical coordinates. Mostly did examples on spherical. I think you'll agree with me by this point, that's the hardest.